Our next speaker is Chen from UC Davis.
Okay. Can you hear me? All right. So I'm PhD student number 20 of Randy, and I put there AKA Penny and Chini because of Randy, because the first few months I joined his group, he always called me Penny. In the first few group meetings, it's very confusing because he'll expect someone to make presentation and he'll say Penny, and then no one goes up, and then he's looking at me. And then 13 years later, I'm still known as Chini on his website, but anyway. All right, so thank you. Thank you, Harry, for setting up the stage for how important it is to have safe driving. So I'm going to talk about connected cars and corridors, I guess the other perspective of it. So when I say cars, in general, kind of, it refers to motorized vehicles, including buses and trucks. And then corridors refer to basically all this infrastructure that has surface transportation near or between population centers. So it includes freeways, bridges, and also light rail. So when they get connected, well, I guess this started back in 1999 when the FCC allocated 75 megahertz of the spectrum in a 5.9 gigahertz range to be used for intelligent transportation systems. So this is for vehicle-to-vehicle and vehicle-to-infrastructure. So, and then in 2004, I mean, around that time, there's standardization body that, work on this, and they defined a MAC layer for that, basically communication, right? So it's a physical layer and the link layer, and it comes under IEEE 802.11p. And then around the same time as well, there's a consortium of automotive industry that came together and defined a higher level stack for this kind of communications, because TCP/IP basically a little bit too clunky for it, and so they defined their own layer, higher level layer, to do the driving safety applications and all that. So there is a plan for US DOT to mandate that all new cars to have V2B communications soon. So obviously now, what does that mean to have connected cars and corridors? Well, the car itself, right, modern car today, itself is a distributed system. I mean, it has about, over 100 control board units on it with processors that can be as powerful as your laptop or a processor that is, like in your PlayStation. So now the car itself is doing a lot of sensing, right? So radar, LiDAR, detecting pedestrian, detecting gap of the cars in front of you. Yes, cameras, right? So you have rear-end camera as well nowadays. And then with the communications capability between cars, you can also have this, idea of virtual front view, where if you are, driving around a corner, you can see beyond that, and the car in front of you who has a camera can stream, video streams to you. So now with connectivity, right, you're enabling this collaborative sensing and detection. Now, what does that mean? Well, now you can have collaborative driving, right? So one of the examples I'm going to talk about later is how does that wireless communication between cars can enable collaborative automated cruise control. It can also enable platooning, basically having a stream of vehicles that are following each other. And the advantage is that then now you can have a smaller gap between them, and you can have higher throughput. Now, as far as the infrastructure is concerned, you can have actuated corridor control, right? So, for example, traffic light, right? Traffic signal light. So instead of having a fixed time signal where you have a fixed time for yellow, green, and red, now you can actuate a traffic signal light. Well, this sounds very much like actually a router, right? A scheduler problem at a network router. So, I mean, moving forward, now it's important to have traffic light control not just for motorized vehicle, but also for non-motorized vehicle, right? So for multi-modal traffic. And you could have a roadside box, like the last picture there, that is broadcasting information, for example, advisory speed limit for cars, depending on the flow rate, right? So at the infrastructure side, you also have a roadside sensors that is collecting aggregate data about flow rate. It has a longer kind of temporal data that you can analyze. And then based on that, and also the real-time detection of the speed and velocity and also acceleration from the cars, now the infrastructure can actually compute what is the optimal speed that you should travel at, and then give that information back to the cars. Why is that useful? Well, so far we talk about safety, right? So obviously that's very important. You want to avoid collision, but besides that, it's also important to reduce congestion and reduce travel time. So having the dynamic rerouting, having you spend less time at the intersection, it translates to minimize travel time and money for a lot of people. It also improves fuel efficiency. So it's really bad, right? If you talk to car companies like Toyota, it's actually pretty hard for them to go beyond what they can do today in terms of reducing your carbon footprint, right? Increasing fuel efficiency. They finally realized that you actually have to couple that, what the cars can do, together with the infrastructure. So why is that? Well, if you have a car that travels at fast speed and then suddenly you stop, you know that that's not very fuel efficiency, right? Not very fuel efficient. What you want is actually the cars maintaining a smooth velocity, right? But there are things that the cars cannot control. Part of it is the green light, right? So if you have traffic lights across different multiple intersections that are actually coordinating with one another, and make sure that you have a smooth, basically if you are traveling at a smooth speed, you can go through all the green light without stopping, then you can reap the benefit of having a constant speed instead of a large fluctuation in speed. And then finally, of course, I mean, one of our dreams is having a self-driving car, right? So if that technology is available, then we can envision that one day Randy will be able to ride in a self-driving Land Rover while updating his Facebook profile. All right, so this is a collaborative project with my colleague, Professor Deepak Gosal in computer science, and Michael Chung, who is an expert in transportation engineering and civil and environmental engineering. And yeah, the current PhD students working on this project, and we also have 3 alumni. One joined Google, one joined Uber, and then one at AT&T now. Okay, so there are just 4 topics that I want to kind of quickly give you a flavor of what we work on. So in terms of collaborative automated cruise control, so obviously for automated cruise control is already out there today. And there are 3 things that the car needs to do, right? After sensing, it needs to do gap control, so how far apart from the previous car, speed control, what is the optimal speed to travel at, and collision avoidance. So the collaborative automated cruise control basically now is getting the data from collaborative sensing, from exchanging information with the other cars. So with that, you can potentially minimize gap, which translates to increased flow rate. And you can also basically have achieve early stopping, right? So if the car in front of you suddenly slows down, you can detect it faster and you can stop earlier. So that translates to enhanced safety. Well, obviously there are challenges, right? So you have heterogeneity in vehicles. So trucks will take longer to stop than a race car, for example. And penetration rate, so not all the cars are equipped with V2V and V2I yet. So not all the cars are sensitive and respond to this type of CACC capability. And obviously, when you design the control loop, we have to worry about local and string stability, right? So you don't want you don't want to overcorrect. You don't want to change the acceleration too quickly and too often. Now, in terms of the sensing part, obviously there's measurement error and there's wireless communication loss, and this all impact the local and string stability as well. All right, so just one quick graph of what we can do. So this is, let's say we have 10 vehicles, and you have the first vehicle brake, right, vehicle 0, and speed up and then slow down. So the top graph is showing the automated cruise control, what happens if you don't share information, there is no communications between the cars. And the bottom graph shows when you have collaborative ACC, and you can see that actually with CACC, you reach a complete stop much faster, and you also track the speed a lot better. Okay? All right, so I talked about impact of packet loss. One of the challenges is that you can have lossy communications. So this is an example of having 30 cars and the speed profile of the first one and also the speed profile of the last car. Even though you track the speed, unfortunately, when you have packet loss, right, as you increase the packet loss, you start to see this instability, right? So you have the speed of the car fluctuate rapidly. And that is something that we would like to avoid. All right, so I won't be able to go through all the details, so if you're interested, we refer you to our manuscript. So once you have collaborative ACC, now you could potentially also do platooning, right? Grouping the vehicles into groups of close following vehicles. Again, I mean, now this you can have a closer gap. You can enhance safety, and with the smooth speed, now you have reduced fuel consumption as well. And especially for highways, you have this slipstream effect, basically reduce the air drag. So, I mean, this is the same technique used in cycling. Also, I think the most important application for this is for heavy-duty trucks, right? So for truck driving on highways. Now, for this to happen, we need to basically design the platoon management protocol. And we found that we can have a platoon with a leader and the followers. So, I mean, I won't go into the details, but I mean, this, at the end of the day, really is a finite state machine. So all the maneuvers that you want to do, you can basically perform using 3 basic maneuvers, merge the platoon, split, and lane change. Right? And you can define each of these maneuvers as a finite state machine. And question? No. All right. So, and I just want to just show it. I won't go into the details, but for each of these maneuvers, it's actually pretty complex in terms of, you have to get the protocol right. And then all the things that we learned as a student now come into play as well, because it is a protocol, design. So you have to make sure that the protocol is correct and efficient. All right, so let me split through that. So obviously, there are a lot of security challenges that are associated with collaborative driving. I mean, there could be different kind of attacks. So application layer attacks can target a specific application. A lot of the work going on right now in the wave security community is to define security protocol, communication protocols. This is secure the communication between the 2 entities. But unfortunately, it won't protect against insider adversary. So I mean, you could still have secure communications, but your endpoint, if let's say, for example, your sensors are being tampered with and you give incorrect information, you can still kind of lead to instability and lead to a failure, or lead your protocol to arrive at a state that is not desirable. So there's obviously also network layer attacks. There are work out there that look at countermeasures. And also system-level attacks like tampering with vehicle hardware and software, as well as privacy leakage attacks. So I won't go into details of this, but I just want to kind of show that there are a lot of still open challenges out there in the area of security challenges for collaborative driving. And the last topic I want to talk about is smart intersections. So as I said before, I mean, the traffic signal light is really like a scheduler, right? As of now, I mean, it's important to differentiate the different kind of or different classes of traffic. So besides motorized vehicles, you also have bikes and pedestrians. Now, this is important, especially for cities like Davis, where we have more bikes than cars on campus. So there would really, I mean, it can be boiled down to 2 parts of it. So one is detection and classification. So existing intersections and existing infrastructure, you have loop detector. You can detect vehicles, but you cannot detect bikers or pedestrians very accurately because they are too light. There are companies like Econolight that look at installing camera, so they do real-time image detection, and they can focus on bike lanes and detect the queue length at the bike lanes pretty accurately, but again, they cannot track pedestrians because the movement are just too scattered and too random. So one of the things that we are working on right now is active detection through mobile devices, right? So all the people, I mean, all the pedestrians, bikers, drivers, you are carrying mobile devices with you all the time, and they are broadcasting beacons all the time. So basically, there is a chance here to look at, how do you do active detection of the presence of, either cars or vehicles or pedestrians by listening to all these beacons. Now, there are challenges here because a user can have multiple devices. There is ambiguity, right? So how do you differentiate between a user that is walking a bike versus passengers that are sitting in the car, and so on and so forth. So we are currently working with a company that is going to give us some boxes that we can put on campus and collect data and then work on this problem. Now, the second part of the second technology that is important for intersection is the actual traffic signal light control. So as I said, I mean, existing traffic actuated TSC are using queue size that are measured using area detector as an input, and then use that to optimize what should be the optimal phase for green, red, and yellow light. So one of the things that we work on is to use a two-state approach. So we use VANET to form equal-sized platoons, and then we can formulate it as a job scheduling problem with equal job size. And then we come up with this oldest job first, and we show that it can reduce delay under light and medium traffic load, and it also performs the same under heavy traffic load as existing algorithms. And currently, we are working on how to extend it to multiple queues and also look at providing feedback like warning and speed advices to vehicles. So I just want to end with this. My group has, the results that we have gotten, obviously we don't have funding to go out and buy all these fancy cars. So all of the research is done using a simulator that is built in-house. There are two components to it. On top level, we have network simulator to implement basically all the packet level activities, sending packets between the cars. And then the lower layer, we have Sumo, which actually is a vehicular traffic simulator, so that we can actually have very accurate car modeling model and also all this collaborative CACC capability that we have built in. So we just released the code this week. So if you're interested, you're welcome to go to the website and grab it. And then lastly, I just want to part with this. I think connected cars and corridors are here to stay. It's no longer just a civil engineering or a mechanical engineering problem. It has everything to do with EE and CS. So for the existing students in the audience, I encourage you to think of it as a component in your problem, right? Especially nowadays. Like for example, this summer, I know Red Pine Signal is a startup company in the Bay Area that just announced that they support multiple wireless protocol on the same chip, right? So potentially you can have your mobile device, your IoT, talking to cars and talking to roadside boxes as well, right? So you have vehicle to X service. So with that, I will end my talk and take questions. Yes.
So one of the things that I'm concerned about when you put all these sensors in cars and you turn on connectivity is the security stuff. In fact, I think, George, you've got colleagues at UC San Diego who did stuff on that. And any comments on how having all cars talk to all the other cars actually impacts potential security and what we can do to try and prevent it, both in terms of design and also in terms of random hack now means I can take control of cars?
So obviously there are a lot of smart people in the automotive industry working very hard on what they call the kind of tamper-proof sensors and things in the cars. That is very, you have to make that secure, right? But that's not enough. That's what my point is, that even that is not enough. Even with securing the communication itself is not enough, because you are building applications on top of it. And that application is in actually coordinating the driving and coordinating. So even from the protocol perspective, we have to be cognizant that you might not be able to trust the sensor data. You might not be able to basically, everything that you do, you have to have a fallback plan. So for example, in the CACC case, right, the natural fallback is that when you detect something is going wrong, right, basically you have to validate. So not just your sensor data, you can validate with messages or information you can get from other devices, for example, right? So you can get speed data not just from your car, but also from your cell phone, for example. So if you notice that something is wrong, you can fall back to just ACC, just a default.
No, I'm more concerned about what happens if I'm driving my car and someone else's car lies to me about where it is or what it's observing. That's more of a concern from my point of view, because I'm not worried about my car being hacked internally. I'm worried about it talking to somebody else's and getting messages that force.
Right. So part of that is that you really have to verify. Right, so you have to have a protocol that verifies the input various ways, not just based on what, and which is actually doable to say with your in-car. Actually, you already have sensing data as well, right, in terms of the gap in front of you and other things. But yeah, I understand your concern, and that's basically the biggest, one of the biggest challenges that when I talk to Toyota and other cars company, there is something that. Yes.
So one question I have is regarding the platooning thing. Platooning, while I understand your logic, can also be kind of dangerous from the perspective of traffic jams. So if the more you platoon, you're actually building an elephant, and if the first guy actually breaks, sort of you see a ripple effect, and sort of the capacity, especially in highways and free flow traffic, is a very nonlinear behavior. And once you hit like even a quasi jam, recovering takes a lot of time.
Correct.
So what's your thought on platooning versus jams?
One thing that I didn't have time to go over is that I talk about the maneuver. How do the cars, based on CACC and communications, achieve the platoon? Either you split or merge and so on and so forth. But you need somebody to tell you what is the optimal size of the platoon. So that you will have to rely on the infrastructure side, because they will have a more long-term kind of history profile of the flow rate of that intersection or that highway segment. And they will tell you basically, at this point in time, this is the optimal platoon size, and that is kind of the input that is given, broadcasted to the cars, and then the cars themselves figure out how to form that platoon of that size. So I didn't have time to show the graph, but basically we show that with that, if we are given, let's say the optimal size is 10, you can form a platoon, and then it could change, and the size is 2, and now the protocol you can just correct yourself and form platoons of 2. Yep.
Thank you. I think we should thank you.
All right, thank you.